Code coverage is a software testing metric that determines the number of lines of code that is successfully validated under a unit test. Code coverage was one of the first methods invented for systematic software testing. The first published reference of code coverage was in 1963 by Miller and Maloney in a paper called Communications of the AMC. Code coverage is a form of white box testing which finds the areas of the program not exercised by a set of test cases. Code coverage aids on both the developmental side and the quality assurance side of software. It helps the developers by checking for dead code and elimination, and it helps in quality assurance by identifying if there were any uncovered test cases. There are a mass amount of tools that can be utilized to check for code coverage in a variety of programming languages. This slide lists just a few recommended tools for some of the more common programming languages. For example, in Java, tools that can be used are Sonar, Eclipse, and inbuilt in IntelliJ. For C and C++, Bullseye coverage and Frog Logic Squish Cocoa. And for Python, coverage.py can be utilized. So how does code coverage work? A test unit or multiple test units are developed and ran against the source code. Multiple test units compiled together are called test suites. When running a code coverage tool after writing a unit test, the tool will use colors to indicate different outcomes of lines of code. So, green highlighted lines of code are fully covered by the test unit. In this photo reference, you can see that super, user ID, MCC, MNC, user category equals prepaid, and return false were fully covered lines of code that were successfully tested against the test unit. Red highlighted lines of code are not covered by the test unit. Looking at the photo reference on this slide, the lines "this service equals true," "return true" are not covered by the test unit. And finally, yellow highlighted lines of code are partially covered. This occurs a lot during if statements due to only one side of the if option being tested in the test unit. As you can see in the photo reference, that case is true here. Both if statements are only partially executed. Code coverage tools determine the percentage of source code covered by unit tests. This percentage is determined by the equation code coverage percentage equals the number of lines of code executed by a testing algorithm divided by the total number of lines of code in a system component multiplied by 100. So let's say that you have 1,000 lines of code and 700 lines of code are executed by a test unit. You would have 70% code coverage. It is in your best interest to obtain 100% code coverage, but in certain cases that may not be possible. Typically, a range of 80 to 100% code coverage is sufficient. So going back to the example I described earlier about obtaining 70% code coverage from 1,000 lines of code, additional test units should be developed to cover more than 100 additional lines of code in order to get to the minimal acceptable range of code coverage. Looking at the picture on the right, you can see multiple projects. The roaming user has 0%, Local user has 54.8% next to it, and policy user has 91.3% presented next to it. The percentage for each of these projects indicate the percentage of code coverage. Therefore, only policy user has an appropriate amount of code coverage. Additional test units should be implemented to raise the code coverage of roaming user and local user. There are 5 types of coverage criteria. The first coverage criteria I will go over is function coverage. Function coverage means that all functions in the source code are called and executed at least one time. In a source code, there may be multiple functions, and depending on the input values used, a function may or may not be called for. The purpose of function coverage is to ensure that each function is called for. So, for example, in example 1 code that is provided on this slide, if our unit test calls the add function just one time, then this would be a complete function coverage. The second coverage criteria is statement coverage. This involves the execution of all these statements at least once in the source code. In a source code, there could be a certain condition that might not get executed depending on the input values. Thus, different input value sets would have to be utilized to ensure each statement gets executed. So, for example, let's look at example 1 again. In this example, if the input values are taken as 2 and 3, the else portion of the code would not have been executed. However, if the input values are 3 and 2, then the if part of the code would not have been executed. So, for a test case to receive 100% coverage, the test unit must execute 3 sets of values, 2 and 3, 3 and 2, and 0 and 0. The third criteria is path coverage. In path coverage, all possible paths are examined and executed at least once. Let's look at example 2. For all paths to be executed, a test unit has to be written for x being greater than 5 and a test unit for when x is less than or equal to 5 in order to receive 100% coverage. The fourth criteria is branch and decision coverage. This involves ensuring that each of the possible branches for each decision point is executed at least once, and thereby ensuring all reachable code is executed, that every decision is taken each way. So, back to example 1, if the value sets are as follows, and you might want to write this down, the value sets being 2 and 3, 4 and 2, 1 and 1. Then branch coverage would be 100%. When data set 2 and 3 is used, then B, which is 3, is greater than A of 2, and the first if branch gets executed. Similarly, when data set 4 and 2 is used, then A being 4 greater than B being 2 evaluates to true, and the second if branch gets executed. Then, with the data set 1 and 1, the else branch evaluates to true, and gets executed, thereby ensuring 100% branch coverage. The fifth coverage criteria is condition coverage, also known as predicate coverage, and this is when each one of the Boolean expressions have been evaluated to both true and false throughout the code. So, back to example 1, and you may take time to write down these data sets to follow along, the data sets being 2 and 3 and 4 and 2. If these data sets are used, then condition coverage would be 100%. When data set 2 and 3 is used, then B being 3 greater than A being 2 evaluates to true. And A being 2 greater than 3 or B evaluates to false. Similarly, when data set 4 and 2 is used, then B being 2 greater than A being 4 evaluates to false, and A being 4 greater than 2 being B evaluates to true. Thus, both the conditions have both the values true and false covered. Therefore, the condition coverage would be 100%. I think it's important to note that condition coverage and branch coverage are often confused with one another due to sounding so similar. Therefore, to clear up the differences, let's take another look at example 3. So, I will give you 2 data sets to write down and to go over branch coverage of example 3. Those data sets being 1 and 1 and 1 and 0. So under branch coverage criteria, using data sets 1 and 1, for example 3, in this case, A and B both are true, so the if condition gets executed. Using data set 1 and 0, in this case, A is true and B would be false, so the else part of the code is executed. So, as we know, the purpose of branch coverage is to get every branch executed at least once, and this purpose is achieved with those data sets. Now, moving on to condition coverage using example 3 and 2 data sets of 1 and 0, 0 and 1. With the data set 1 and 0, in this case, A is true and B would be false. With the data set 0 and 1, in this case, A is false and B would be true. And the purpose of condition coverage is to get each of true and false for every condition executed, and this purpose is achieved here. So, did you notice that the if part does not get executed in condition coverage, but it did get executed in branch coverage? And that right there is where condition coverage differs from branch coverage. Why do we use code coverage? Code coverage helps measure efficiency of test implementation. It offers a quantitative measurement. It defines the degree to which the source code has been tested. Good unit tests catch defects in the future. Unit tests are automated tests, so if someone adds to the code in the future, the code is still being tested by all the previously written test units. Therefore, it may be more obvious if a defect is introduced. Another reason is that systems with good unit tests improve over a period of time. And that is because if more unit tests are being written, then less defects will be observed. With good unit tests, the developer can have more confidence progressing the code because the test units will be able to find a broken functionality. Some challenges that we face with using code coverage are that codes containing massive amounts of logic are just more difficult to test. If statements can become quite tricky. Not having proper asserts. It's good to have reviews to make sure that you have proper asserts. Certain parts of applications are not designed for unit testing. Old frameworks like web and database, they're not designed to be unit tested. And one of the biggest challenges, in my opinion, is that involves writing tests just for coverage. And what I mean by that is that this is where writing good test units are essential. A person can write a test unit that covers a lot of lines of code to pass coverage criteria, but it might not aid in ensuring proper functionality. So, for example, if there is a portion of code that calculates a value, you can still get great code coverage without verifying that the value output from the calculation is actually correct. So it's important to write a test unit that verifies and checks the expected output of the equation to ensure not only code coverage, but also proper functionality. Good code coverage is a function of good test units. So if code is built on irrelevant test case coverage, then the software will compromise on quality.